Now I am taking the topic, the electron theory of ferromagnetism. Ferromagnetism has two theories, one the electron theory and second the domain theory. Here I am telling you first the electron theory of ferromagnetism. The ferromagnetic material are strongly attracted by the applied magnetic field. So they have very high magnetism when the magnetic field is applied on them. The substances which are strongly attracted by external magnetic field are called ferromagnetic substances. Ferromagnetic substances. Now I give you example that suppose this is a plate on which we are having. This is the ferromagnetic material. This is ferromagnetic material. This is in absence of magnetic field. In absence of magnetic field. Now suppose we are having these two magnets here. This is north. This is another magnet. This is now south, and this plate is placed here. Then what happens that the maximum is collected so you see that this material is collected near this north pole and the south pole, and just at the center there is very few amount of the ferromagnetic material. So this is strongly attracted by the magnetic field. In presence of magnetic field. The substances which are ferromagnetic are iron, cobalt and nickel. The ferromagnetism is strongly exhibited by iron, cobalt and nickel called ferromagnetic material. Ferromagnetic material. The reason is that in case of iron, cobalt and nickel, the 3D subcells are not complete. I have told you that the single electron provides the magnetic moment. the magnetic moment due to single orbital electron is given as, this is now m equal to n into mb, where n equal to 1, 2, 3, 4 and so on, principal quantum number, principal quantum number. And this mb, this is Bohr magnetron. Bohr magnetron 9.27 into 10 raised to the power minus 4 joule per Tesla. This is so much. Now this iron nickel cobalt, in iron, cobalt, nickel, the 3D subcells are incomplete. Now this iron, for iron Z equal to 26. The Z atomic number is 26. So now as we fill them, the electronic contribution will be this now 2, 8, 14 and 2. So now in 3D subcell, this is now complete, this is complete, this is also complete, but this 3D cell is not complete. So this should have how much? 3D subcell. Now this we are having the 14 electron. So this is the 3s2, 3p6 and this is now 8. Then this is now your 3d. Now this is now 8 and this is now 6. 14. So how we have? This is like this. And 3p6, this is like this. Like this. This is now 3p6, now 3d10. Now this is 1, 2, 3, 1, 2, 3, like this. This is now one electron in each. This is now 5 and then this is now 6th electron. So there are 4 electrons are unpaired. This is now 6. So now in this 3 electrons are unpaired. In 3D subcell, 3 electrons are unpaired. Three electrons are unpaired. Now this is your 3s2, this is 3p6 and this is now 3d6. This is about this iron. And now then for cobalt. Now for cobalt. Cobalt. For cobalt. Now this Z equal to 27. 27. So this is now your 2. This is now your 2, 8, 15 and 2. So again this third cell, 3D cell. So now in this 3D we are having this. Now this 3S2, 3P6, 3D cell. So this can be filled up like this one. That this is 3S2. 2 electron, now this in this way, this is now your 3p6 and then 1, 2, 3, 4 and 5. This is now 1, 1, 1, 1, 1. This is now like this. Here the 3 electrons are unpaired. 3 electrons are unpaired. This is 3d7. 3d7. So 3 electrons are unpaired in 3D subset. 3D subset. Now for nickel. Now this Z equal to 28. So we can have this 2, 8 and then 16 and then 2. So this 16 can be have this 3S2, 3p6 and 3d8. 3d8. So now in this now 3s2. This is now 3s2. This is now like this. Now then 3p6. This is now 3p6 and here this is now 1, 2, 3, this is now 4. So this is now 1, 1, 1, 1 and 1 and this is now your this so and this now so. Here these 2 electrons are unpaired in 3D cell. This is now your 3d8. 3d8. The 2 electrons are unpaired in 3D subset. So what we are having that in case of iron there are the magnetic moment is due to these 4 electrons and this cobalt due to these 3 electrons and in case of nickel because of these 2 electrons. So they are having their own magnetic moment which is very high. due to unpaired electrons in 3D subcell. The atoms have large magnetic moment. So this is why that when this magnetic field the atoms have large magnetic moments. In absence of applied magnetic field, the atomic magnets are randomly arranged having no magnetic moment, no magnetic moment. So this is what that suppose this is the material and the magnetic moments of these like this. Like this. So the net magnetic moment is 0. Is 0. So here this applied magnetic field B is equal to 0. B equal to 0. As the magnetic field is applied, when magnetic field is applied, almost all atomic magnets are aligned in the direction of magnetic field. Direction of magnetic field. Due to thermal energy, some magnets atomic magnets are not aligned. So this is what that we are having this sample this is now magnetic field being applied in this direction, then these atomic magnets are aligned like this. Now some of them may not be aligned. This is now the magnetic moment, net magnetic moment is not equal to 0. Net magnetic moment is not equal to 0. This means that they are getting very strong magnetization in the direction of the magnetic field. The material get magnetization in the direction of magnetic field, in the direction of magnetic field. It means that they are having very high intensity of magnetization. So intensity of magnetization I, this is equal to positive and very high. So this we are having like this. If I take I and this is now applied magnetic field H in this direction, then we are getting in this. So this is not like this one. The curve is not the straight, but this shows that at this position the I is maximum value. Susceptibility is positive. Chi is equal to positive and very high value of chi. Relative permeability mu r is very greater than 1. So the magnetic permeability of ferromagnetic substances now this we are having this mu r equal to mu upon mu naught. Since mu r is very greater than 1, so mu is very greater than mu naught. The magnetic permeability of the ferromagnetic substances is very large in comparison to the magnetic permeability of the free space. The susceptibility So this chi is equal to C upon T minus Tc. This is called Curie-Weiss law. Curie-Weiss law. Now here C is Curie constant, Tc, this is the Curie temperature. Curie temperature. Curie temperature. So this Curie temperature is the temperature at which the ferromagnetic material converts into the paramagnetic material. This is when the magnetic field is applied. As the magnetic field is switched off, as the magnetic field is switched off, the ferromagnetic material shows residual magnetism. It means what? That when the magnetic field is switched off, even there is the magnetism that is remains inside the material. So after switching off the magnetic field, the magnetization is not zero. So they also exhibit the residual magnetism in absence of when the magnetic field is switched off. Shows the residual magnetism. Now the example of this one, all the ferromagnetic, all the iron-like material shows this ferromagnetism, and this is due to the 3D subcells which are incomplete and having the unpaired electrons. So now I will show you the presence of the magnetic field. How does it happen in this case? This is now suppose now this is the applied magnetic field. Now here we are having then they pass like this. These are the magnetic lines of force. So maximum are passing through this material. Maximum are passing through this material. And also you can see that this inside they are having like this. And they are like this. This must be nearest to this one. So you see that all the magnetic lines of force which are due to this induced magnetism, they are also supporting to this external magnetic field inside the material. So this we can show. This is the magnetic field B. So this shows that maximum lines of force pass through this ferromagnetic material. So this is all about the electron theory of the ferromagnetic materials. So thank you very much.